Okay, another researcher is in Finland, Dr. Eugene Podkletnov. I have corresponded with him a number of times. I haven't in the last couple of years, though. But his situation was he is a material scientist working in Finland, and his expertise is in developing superconductors. And so they had developed this superconducting ring, and they were playing around with it. Let me see, I think the next picture might, yeah. So this ring, they would suspend it. It was cryogenically cooled, first of all, so it's very cold. And it would be suspended in a magnetic field, so it was floating. And they were just experimenting with it. And according to what he said, that as they were playing around with this in the lab one day, someone was going home from work upstairs, I guess, came down and came into the lab to see what they were doing, and happened to be smoking a pipe. And they noticed that the smoke would drift over and go shoot straight up above this device. And that got them curious. So they set up an apparatus where they could put a weight over it and weigh it. And they found a weight reduction when this thing was spinning. Unfortunately, I don't think they ever turned it to spin it the other way, because that would have been interesting. But they do know this. Anyway, so he actually published a paper talking about this 2% weight reduction. But he was smart enough not to say, hey, you know what, I just created gravity. What he said is he's shielding gravity. People would accept that. Well, later on, he went on to develop this apparatus where, again, it involves a superconductor spinning and cryogenically cooled, but then they would hit it with a high pulse electric charge and a very short duration pulse, and out would come a gravitational pulse. And he said if you put your hand in front of it, it felt like a puff of air. But depending on the duration of this pulse of the signal, if it was very short, they could get a very powerful pulse coming out. And but he said, whatever you do, don't put your hands in the back of it. It's the danger zone. If you're holding a pencil or anything in your hand and you reach back there, you might find that the pencil is part of your hand. It's all melded together. Some of you might recall the Philadelphia experiment. Okay, that's what happened. So this device he had produced pulses that can pass through all materials, but if it's not too powerful, it won't cause any damage. At low power, it can pass through object distances, virtually no beam divergence, kind of like a laser. And little energy was lost. And one of the thoughts he was thinking about, his interest was in space travel. He thought, you know, if we have one of these things, we could aim it at a satellite, and if we wanted to move it to a different altitude, we could push it up with these pulses. And that's one of the things he thought could be used for. But he said that as far as his experiments, the voltage rise, the rate at which it would rise was very important. If it was too fast, it could become powerful and actually damage the buildings and even the apparatus itself. But at full power, the metal plate situated just in front of this, just a meter in front of the chamber, they could punch a hole in it. And a 2-inch thick plate, they could bend a plate, metal plate. Now, you would think that would have a tremendous kickback, but that was one of the interesting things about their discoveries. There was no equal and opposite reaction. That defies the physics that I learned. The other thing is they measured the amount of energy that was dissipated by this beam, and it dissipated more energy than what they put into it. And so when asked about that, he says, well, I'm not a theoretical physicist, but maybe this gravitational field pulse is somehow causing subatomic particles to release energy. That was the only theory he could come up with. As I said, the experimentalists are way ahead of the theorists right now on gravity propulsion. He did measure the velocity. He was curious how fast it travels. And if you ask a physicist, how fast does gravity travel? 99.9% of them will say at the speed of light. Okay? So that means if the sun ever disappears all of a sudden, at the speed of light, we would be, 9 minutes away from disaster. But we wouldn't know it for 9 minutes. Well, guess what? He set up some transducers and measured, they were like 1,200 meters apart, and had an atomic clock so he could measure very accurate timing. and he determined that the speed was 64 times the speed of light. And in my second novel, my character made use of that, because he asked the alien, well, here you are, you're kind of overlooking the Earth here, and your home base is 50 light years away. How do you get any decisions made, you know, from home? Because you'd send out a request and take 50 years for it to get there, and hopefully it could turn around right away. It'd be another 50 years. So it'd be 100 years before you got an answer. And Quellen said, well, actually, we send our messages out on a gravity pulse beam, which is a carrier wave, if you will. And so it doesn't take that long, a couple years. So anyway, I'm the first one that ever employed that, by the way. So how do they work? There have been people, credible witnesses like astronauts and other people who have seen these things and reported really amazing things. So they've seen, and they've actually measured the rate of acceleration to be 100 Gs. They've been able to look like they make right-angle turns. They travel supersonically with no shock wave. They shake metal shingles and roofs. If you ever saw Close Encounters of the Third Kind when the mailboxes were shaking, that's true. That happens. And of course, if you're driving a conventional car, just like in Close Encounters, the engine quits because the ignition system fails. Now, the smart thing then is to own a diesel, because as far as I know, that's not affected. Change colors. People see them changing colors. Cloaking. It'll be here, and all of a sudden it's gone. It's like it just cloaked itself. You know, like the Klingons. Freezing ponds. They've come upon an area where it was a shallow pond, and a UFO just left, and the pond is frozen. It's not wintertime. So how do they do this? That's, you know, Arthur C. Clarke said, any significantly advanced technology will appear indistinguishable from magic. And to us, what they're doing looks like magic. But it's all explainable. And one of the things I do in my books and my lectures is I never invoke anything that you have not had in high school science. So I don't talk about multi-dimensions, wormholes. It's all stuff that you probably had in your science class. And I figure if you can't explain it that way, then it doesn't happen, you know. But you can. So that's what I'll do. So how is it, if they can travel and accelerate at 100 Gs, how come the occupants aren't squished? You would think they would be. Our own aircraft, we're limited to about 8 or 10 Gs, and that's with a G suit. And I think there was an Air Force colonel that was trying to determine the limits of human endurance on Gs, I guess, years ago. I remember it out in in fact, I think it was in White Sands. He rode a rocket sled, and it decelerated at something 30 or 40 Gs. And his eyeballs came out of their socket, and he almost died. That's 30 or 40 Gs. So, so how do they do 100 Gs? Well, to explain that, we do this thing that Einstein always liked to do. It's a thought experience. If I could get someone to volunteer in the audience, that little kid back there in the blue suit, I'm going to put him up in that rocket nose, and he's got a cell phone, I know he does, and I have one. So I am going to light the fuse, and off he goes. And I'm watching, and I'm talking, his name is Robbie, by the way. I say, Robbie, what's happening? And Robbie says, well, I'm being pulled down again in my couch because the G meter says I'm accelerating at 4 Gs, and I can hardly move. And I'm watching him, and that rocket, all of a sudden the flame sputters out, but he's still coasting up. I say, Robbie, what's happening now? And Robbie says, well, now the G meter says 0, and I'm tending to float out on my couch, but I have straps on, so I'm okay. And I'm watching him, and okay, now it's coming down. I said, Robbie, what's happening now? He says, nothing's changed. It's still 0 Gs, and I'm still tending to float in my couch. And I said, but Robbie, do you know you're accelerating at 1 G? And if we did this experiment on Jupiter, you would be accelerating at 40 Gs, but yet you have no sensation of it. You are free falling into the gravitational field. So what if you could build a craft that could develop a gravitational field, let's say a negative field, and you could free fall away from it? Wouldn't matter how many Gs you do it. You're free falling. And if you decide to change direction and you vector your field this way, all of a sudden you're going that way. You free fall in that direction. So there's no sensation. And that's the beauty of gravitational field propulsion. You can accelerate at any rate you want. And I just showed you how it's possible to create gravity. Okay, how about shaking signs and ignition failures? Well, that is simply an effect of strong magnetic fields. There are strong magnetic fields around these things. Changing colors. That is something called synchrotron radiation. In the process of creating these gravitational fields, it's not 100% efficient, and they actually end up wasting energy, if you would, radiating energy, and it's a whole spectrum of wavelengths. This is why I told you at the beginning, do not stand under a UFO and do not touch a UFO, because there's this radiation coming from it. And so the synchrotron radiation is an example of that. And we didn't discover that till we built our first synchrotron. And what happens is if you have an electron or a charged particle, and if you accelerate it at a changing rate of acceleration, it emits photons. That's the synchrotron radiation. But anyway, it can be a whole spectrum. It can be very dangerous. It could be X-rays, gamma rays. And here's when we discovered it, in General Electric in 1946, when they built their synchrotron, they noticed this light coming out, and they figured out that's what caused it. It's also generated in space. The Crab Nebula, that blue color, is an example of synchrotron radiation.